Welcome back. Now that we have the some ideas and terminology under our belts, we're going to do some actual hypothesis testing. In this section, we'll be testing hypotheses about a population proportion, so a claim about a proportion of a population. Now, the basic idea of hypothesis testing that we actually haven't even talked about yet is that when observed results are unlikely under the assumption that the null hypothesis remember that's H naught, is true, we say the result is statistically significant and we reject the null hypothesis. So hopefully you remember from the last videos that we start out assuming the null hypothesis is true. And you have to start out somewhere. And you'll see as we go on and do hypothesis testing that we're going to use the statement in the null hypothesis. So anyway, so we use it, we assume it's true so that we can use it, and then if the results, or the observed results, don't, let me just say this very informally, if they don't tally with our assumption that the null hypothesis is true, then we're going to reject the null hypothesis. Okay, so what do I mean when I say, what if we observe things that don't tally with the null hypothesis being true? Well, if the results are unlikely, in other words, low probability, so we're going to have to do a probability check on them, but if they have low probability of being true when the null hypothesis is true, then we're going to reject the null hypothesis and say, hey, that assumption probably wasn't a good one. So yes, we start out assuming that the null hypothesis is true, but we have a way of rejecting it if the results don't support that assumption. Okay, so let's talk a little bit about population and sample proportions. So remember, a number that describes a population is called a parameter. So the parameter we're interested in making a claim about or investigating a claim about is this one that we've called P, which is the number of individuals in the population with a characteristic divided by the total number of individuals in the population. That's just what a proportion is. And of course it can be expressed as a percent. The same number, if you get it from a sample, remember a number that describes a sample is called a statistic. So the proportion of a sample with a characteristic would be, and we've typically called that p hat, the number of individuals in the sample with a characteristic divided by the number of individuals in the sample, and the letters we've used for those things typically are x and n. So lowercase n has typically represented the sample size, and then x is the number of individuals in the sample with the characteristic. Remember that when you get a statistic like this p hat from a sample, when you get a statistic as an estimate of the population parameter for the same, the same thing, the same characteristic, we have what's called a point estimate of the population proportion P. Note that for different samples of size n, so even with a particular size sample, size n, you can get different samples by just grabbing a different, batch of n items from the population. So different samples are going to produce different values for p hat. So p hat can be thought of as a random variable called the sampling distribution of the sample proportion. So the probability experiment that p hat is a random variable for is the experiment of taking n people or whatever out of the population and getting the sample proportion. And you get a different answer for every, potentially a different answer for every different sample. The reason I mention that is we need to know that the sampling, that this p hat thing, the sampling distribution of the sampling proportion, is approximately normal. Its mean is the same as p. Now, so p is the actual population proportion. Excuse me. And the standard deviation for this random variable is sigma equals square root of p times 1 minus p over n. We're going to use the fact that this is normal. That's what allows us to use the tables in the back to determine probabilities. Something else I need to mention is that p hat is normal provided that the sampling is random, that np times 1 minus p is greater than or equal to 10, and that the sampled values are independent of each other, which is going to happen when the sample size n is less than or equal to 5% of the population size. I'm not going to do a whole lot with having us look at this stuff, but I needed to mention it because in the homework it'll ask you sometimes to verify that this hypothesis testing that we're going to do, is it valid? Well, we're going to be doing this hypothesis testing based on p hat being normal. How do you know p hat's normal? Well, it's going to be approximately normal provided these things are true. So if the homework asks you, verify that the hypothesis test is valid, what they're asking you is to verify that stuff. Okay, so anyway, you might want to make a note here that so that you can come back to that if the homework asks you about that. Okay, let's see an example here then of a population proportion. A politician wants to know if a majority, more than 50%, of her constituents are in favor of a certain policy. So the hypotheses to be tested are, so again, the alternate hypothesis, that's the one the person's thinking about, what they want to investigate. So her hypothesis, or what she needs to know is that proportion actually greater than 0.5? The null hypothesis is always going to be the same statement with an equals in there. Notice saying that the null hypothesis, saying that 50% of her constituents are in favor of the policy, is saying there's no difference between the number of constituents that are in favor and aren't in favor. Okay, a politician obtains a random sample of 1,000 registered voters in her district and finds that 534 of them are in favor of the policy. So that gives us a point estimate of, so we don't know what p is, that's what she wants to investigate. She's at least got a point estimate now for the population proportion. So for this sample, she has that 534 out of 1,000 are in favor. So that gives her a point estimate of 0.534 or 53.4%. And so the question that we need to go on and consider is, if the true population proportion is actually 50%, is it likely that we would have observed what we did? Would it be likely that we'd get a sample where the proportion is actually 0.534? This is the crux of hypothesis testing, And we'll come back and look at that question in the next video.